no signal to come again. Like, yeah.
Just turn green.
Oh, okay. All right. Okay, so let's start in the interest of time. Good morning, everyone. Welcome to Basin Depends. I've been his advisor for the past 3 years. He joined UCLA as a PhD student in 2007. And his research in the past 3 years has been broadly in the area of spectrum sensing, but from the protocol level perspective. Okay.
Thanks, Professor.
You're welcome to ask any questions.
Hi, my name is Zemko Brown. This is presenting my work here at Course Lab with Professor Daniela at Cambridge. And the title of my work is Traffic-Aware Multi-Channel Multi-Stage Spectrum Sensing for Dynamic Spectrum Access. First, this is an outline of this talk. I'm going to give a brief introduction. Then I will talk about my the problem statement and the research I was doing regarding multi-channel spectrum sensing algorithms. And later I will talk about the effect or the impact of incorporating primary user traffic information in algorithm design. And the next step is to talk about how accurately can you actually estimate the primary user traffic. Then I will conclude the talk with a summary of the contributions. So first, the introduction problem statement. There's an increased demand for wireless connectivity. People want to watch Netflix on their phones, download torrents via Wi-Fi, watch TV channels that get broadcasts through radio. And this will make the spectrum so scarce. And one of the ways to solve this problem is through the concept of cognitive radius or dynamic spectrum access. And this concept basically states that a user, or in this case I will refer to that user in this talk as a second user, this user scavenges or looks for parts of the spectrum that are vacant. And typically the spectrum is usually already licensed by the FCC for a user. I will refer to him in this talk as a primary user, but this user is either spatially or temporally unavailable. So the second user finds the spectral vacancies through a process called spectrum sensing, and this is an example of how it works. So this is, for example, the frequency spectrum. You have primary users here, here, and here, and you have vacancies here and here. And what happens is the second user senses for these vacancies, finds them, and starts operating on them. The typical problem is the traffic of primary users is very dynamic, so the second user has to keep on sensing to make sure that he's not occupying spectrum that is used by an incoming primary user. So, for example, after a period of time, the occupancy of the spectrum changes, and the second user has to redo the sensing and find the new windows. Yeah, find a new vacancy and transmit on it. In typical spectrum sensing algorithms, there are 3 metrics that are usually of interest. You want to maximize the throughput that the second user can achieve. You want to minimize the collision between secondary users, primary users, and you want to minimize the power consumed by the second users. Now I'll talk about spectrum sensing algorithms and the parameters that usually designers put into perspective. So if you look at the protocol stack, I'll start at the channel level. You look at the number of channels, the occupancy per channel, the traffic characteristics of the primary user, and the bandwidth per channel. And at the sensing radio, usually researchers look at whether this radio is narrowband or wideband. At an upper level, which is the physical layer of sensing, usually people consider different sensing techniques. There is energy detection or cyclostationarity detection and so on. And usually these techniques are modeled as a relationship between the sensing time and the probability of false alarm and misdetection of the existence of a primary user. At an upper level, the sensing map, people consider collaboration, multi-stage sensing, like I'm doing in this work. And finally, at the application layer, people consider secondary user traffic and buffering. I'll give a brief example of how spectrum sensing would happen in a real-life scenario. So in this situation, the x-axis here is time, the y-axis are 4 channels, and the secondary user is trying to find spectral vacancy. So let's say, for example, the second user would start at channel 1. So the second user would first sense the channel, find the vacancy, and transmit on it. The green blocks here indicate that a primary user exists. So for the next time slot, the second user would sense the channel, find that it's occupied, leaves the channel, finds another one, and transmits. But because this sensing, the sensing algorithms are not perfect, what happens is you always get false alarms and misdetection. So just as an example, for this coming time slot, the channel here is vacant, but for some reason, the second user thought that, had the false alarm from the sensing outcome and had to leave the channel. So that's one problem with spectrum sensing algorithms. Here you have lost throughput, okay, because you left a perfectly idle channel. Another problem is probability of misdetection. That is, a primary user might be there, but the second user would think that there is no primary user because of the sensing outcome. So in this case, what would happen? The second user would start transmitting with the channel, same time with the primary user, and the collision happens. So in this work, I'm basically trying to actually answering 3 questions. The first one is, when you have a positive sensing outcome, which can be caused by actual existence of a primary user or a false alarm, shall you keep on sensing or shall you switch to a new channel? And this was clear in this example here where you left a channel that is already idle, which costs you throughput. The second question is, looking at channels number 2 and 4, as you can see, the occupancy of the primary user is much less than channels 1 and 3. So obviously you would have reached much higher throughput if you focused more on 2 and 4 instead of 1 and 3. So the second question is, how does knowledge of primary user traffic statistics benefit your metrics performance? And the third question is, okay, so if you reach the conclusion that actually primary user traffic statistics can help, how accurately can you estimate these statistics? So I will proceed to the first question. Positive sensing outcome, do you sense or do you switch? And we published 2 papers at Journal at Transaction on Behavioral Technology and a conference at DICEPAN. And the title of this part is Multi-Channel, Multi-Stage Spectrum Sensing Protocols for Dynamic Spectrum Access. I'll give first an example of how this works. First of all, this algorithm this idea was proposed by IEEE 802.22, where you have an extra stage of sensing after you find a primary user. But we expanded this case for multiple stages, looked at multiple channels, and considered the traffic for secondary and primary users. So I'll give an example of how the algorithm would work. Again, the green blocks here are primary users, and the second user starts at channel 1. So here, the second user senses the channel. Assume that a false alarm actually happened. If this was a single-stage system, the second user would have to go to that next channel. But in this case, the second user stays in the same channel for another stage. So it goes to stage 2 of sensing. So assume that stage 2, the sensing came out with the right result and there is no false alarm. So the second user goes back to stage number 1 and transmits on the channel. Now, as you can see here, you save throughput by not leaving a channel that is perfectly vacant. This is the good side of multi-stage algorithms. The bad side is, in this case, assume that the primary user actually arrived. It will take the second user 2 stages in order to leave the channel, so you have more collisions. The main problem we're trying to solve is the imperfectness of the sensing algorithms. What happens is you get false alarms and misdetections. An obvious way, a way to solve this is by increasing your sensing time, because usually for these techniques, higher time results in more correct sensing outcome. The problem is there's a compromise, because if you keep on increasing your sensing time, the actual throughput that you end up using decreases. So multi-stage algorithms, they provide you with degrees of freedom that are the number of sensing stages, the sensing method per stage, the sensing time per stage. So with all of these degrees of freedom, you reach a better compromise between throughput, collision, and power consumption. Regarding the objective of this work, we are looking at three metrics, as I mentioned before: throughput, collisions, and power consumption, or energy per transmitted bit. And we created a mathematical framework based on discrete time Markov chain that models the radio configuration, whether it's narrowband or wideband, the sensing techniques, which is basically translated in the form of the relationship between sensing time, probability of false alarm misdetection, and the secondary user traffic model and the primary user traffic model, and the number of channels allowed for access. And regarding the assumptions that we have, these are typical assumptions in literature for NEC algorithms for dynamic spectrum access. First, we assume that primary user and second user, the traffic follows the Gilbert-Elliott model, which basically states that the average on time and off time are geometrically distributed. We assume that there's one pair of second users, because, I mean, assuming more than that, assuming that you have a network of second users for this algorithm would just scale the results, so you wouldn't really see any surprising or interesting results for now. And so assume that we have one pair of second users, one-way traffic. We assume that the second users have a buffer of size B packets, and the primary users and secondary users are synchronized in time. That is, they arrive and depart at discrete time. And collided packets are discarded. Regarding the protocol we're looking at in this work, this is, I mean, basically this part is the multi-stage sensing part. You, stage one, you sense, then you transmit. If there is a positive outcome, you go to stage two, positive outcome, you go to stage three, otherwise you return back to stage one. At the very end, there's a quiet phase, because, I mean, this quiet phase, the second user keeps on sensing for the whole time slot, so the probability of false alarm or misdetection is really low. So the motivation behind it is that the second user, before leaving the channel, would be really sure that there is no primary user there. And if the sensing outcome is positive, the second user moves to another channel and does pre-sensing, which is, again, it's one state that is only sensing, no transmission, to make sure that no collisions, or collisions would happen with a very low probability. We looked at different permutations for this protocol with and without quiet stage and pre-sensing stage. I already showed results for that in the quals, and I have the results in the publications. Now I'll talk about the model. As I said, it's a Markov chain model. The state basically has information about the second user traffic, primary user traffic, what channel is used, and the buffer, the number of packets in the buffer, and the stage at which the second user is at. And the metrics are calculated as a function of the stationary probabilities that are derived from the Markov chain model. And there is the throughput, the collisions, and the power consumption. Regarding power consumption, there are two parts. We model the power spent on sensing, because in the second users, usually there's a radio dedicated for sensing, which costs a lot of power. So we this part translates this power. This part is concerned with the sensing radio, and this part is with the transmitting and receiving radio. Regarding this third metric, in order to get figures for the power spent on sensing, the power spent on transmitting, and the power spent on receiving, we refer to this work from a journal on solid-state circuits. So Park, basically,